Jai Hind everyone, my name is Nandita Goyal and today I'll be covering the topic some general identities on set from discrete structures and theory of logic subject. The contents that I'll be covering in my lecture include laws of the algebra for sets, then the laws include Idempotent Law, Associative Law, Commutative Law, Distributive Law, Identity Laws, Involution Laws, Complement Laws and De Morgan's Laws. All these laws hold for sets. So, we will be discussing all these laws in relation to set theory. So, the laws of algebra for sets, all these laws will be holding for the operations which include union, intersection and complement. All these laws will satisfy for these three operations. So, coming to the first law, that is idempotent law. The idempotent law says that if we have a set A with certain elements and we take the union of this set A along with A itself, then the result will be A. And if we check the same law for the operation intersection, it says that if we have a set A and we try to calculate its intersection with set A itself, then the result will again be A. Let's verify this law using Venn diagram. So, suppose this is the universal set U and we have a set A in this. Now, according to the first law, that is the A part, if I take set A's union with set A itself, that means the region will be set A and its union again with A. So, the output will be this entire region which is nothing but set A. This is when I am talking about the union operation. Same way, if I try to find out that what will be the resultant of idempotent law if I work on set A for intersection, then again we will try to verify it using the Venn diagram. So, this is my universal set U. I have a set A and I again try to find out the intersection of this set A with A itself. So, first A will give me this region. Then its intersection with A means again the same region. That means the output for this will again be the set A itself. This is for intersection. So, we can say that if I am talking about idempotent law, then both the laws for union as well as for intersection will hold good. Now, moving to the next law, which is known as associative law. We have both the parts, that is 2A, which is associative law for the operation union, and 2B, which is showing the associative law for operation intersection. So, here we are talking about three sets A, B and C. A, B and C. That means we have a total of three sets A, B and C. And what we are trying to check, we are saying that if I take the union of two sets A and B and then I find the union of the result with set C, that will be same as if I take the union of set B and C and I try to combine it with the union of set A. So, let's verify this law using the Venn diagram. First of all, I'll draw the Venn diagram for the left hand side. So, this is my universal set U. Okay, now I have a total of three sets, that is A, B and C. This is my set A, this is my set B and this is my set C. Now, the first part of the law, that is A union B. A union B means all the elements of set A and all the elements of set B. So, if I try to show it in my Venn diagram, it will be something like, I'll show the entire set A and entire set B. Now, the result is this one and I have to take its union with set C. So, that means all the elements of the result, that is A union B, as well as all the elements of set C. That means if I try to show it with the help of the diagram, this will be something like this. That means the entire region which is being depicted by the left hand side is this region. The entire thing inside this region. So this is showing what? A union B union C. Now let's verify that whether this is same for the right hand side as well. So if I draw the Venn diagram for RHS, again I have the universal set U and I have three sets A, B and C. Now first of all I'll find the union, that is B union C. So if I try to find out B union C, it means all the elements of set B and all the elements of set C. So B union C will be entire set B and set C. Now this is my B union C, this entire region. Now I want to find out the union of the result with set A. So this is my result for union of B and C, and I will find out the union with set A. That means I'll combine this result with set A as well. So again, if I see what is the output is this entire region, that is set A, B and C. This is A union B union C. Now if I compare my left hand side with the right hand side, these both are equivalent. That is why the first law, that is 2A for associate, which is showing the associative nature, holds for set theory. Now coming to the second part of this law, where we are trying to check the law for intersection part. Again, what the law says, that if I take the intersection of two sets A and B and then I combine the result with C with intersection operation, this will be the same as B intersection C, and the result when it is combined with A with the help of intersection operator. So to verify this law, we'll again draw the Venn diagram for left hand side. So if I draw the Venn diagram for left hand side, I am talking about three sets, that is A, B and C. Now this is my universal set U. I have three sets A, B and C. Okay. Now first I'll find out A intersection B. So A intersection B means the common part in set A and set B. That is the common elements of both the sets A and B. So if I want to see the intersection part of set A and set B, this is the common region which is there for A intersection B, this entire region. Now if I want to find out the intersection C region with this result, now this is the entire set C and this is the result which I have got, that is A intersection B. So now combining this with C, so what is the intersection in A intersection B and intersection C? So what is the common region? This is the center one, is the only common region. This is the only common region, which is A intersection B intersection C. So this center part, this gives me A intersection B intersection C. Now if I talk about the right hand side for the same law, this is my universal set U. Again, I have these three sets A, B and C. Now, first I'll find out B intersection C. So if I find out B intersection C, that means the common elements of set B and C. So these are given by this region. And now I have to combine this result with set A with the help of intersection operation. So if I check A intersection B intersection C, so only this center region, this is the common region. So this actually is giving me what? A intersection B intersection C. So now if I compare both these regions, they are the same region. So what can I say? I can say that this 2B also holds good for set. So we have verified the associative law for both intersection and union operation. Now moving to the next law, that is the commutative law. Again, we will be verifying commutative law for both union operation as well as intersection operation. So commutative law says that if I have two sets A and B and I take the result as A union B, this will be same as if I take the result other way, that is B union A. Now to verify this, let's draw the left hand side using Venn diagram. So here we will be talking about only two sets, that is A and B. So this is my universal set U and I have two sets, that is A and B. Now if I want to find out A union B, this will be nothing but all the elements of set A and set B. So if I show it with the help of Venn diagram, I will show the entire region for set A as well as set B. So this shows A union B. Now if I change the order of this union, that is I want to find out B union A. Now what will be the region which will be represented by the right hand side? So we have the universal set U, A and B. Now B union A is nothing but a combination of all the elements which are there in the set B and the set A. So again, if I want to show it with the Venn diagram, it will represent the entire region, that is this one. All the elements of set B and all the elements of set A. So this is my B union A. So my LHS is same as RHS if I check it with the help of the Venn diagram. So I can say that the law 3A holds good that for union operation, that is commutative law is valid for sets for union operation. Now the part 3B shows the same law for the intersection operation, that is A intersection B is equivalent to B intersection A. If I have two sets A and B and I want to find out the intersection and even I change the order for intersection, that means I will get the same region using the Venn diagram. So I will verify it using Venn diagram. First I will show the left hand side. This is my universal set U. I have set A and B over here. Now since we are talking about intersection, intersection means the elements which are common to both the sets A and B. So what are the elements which are common to both the sets, or what is the region which is being represented by A intersection B? This is the region which will contain all the elements which are there in A as well as in B. So this region is nothing but A intersection B. Now let's draw the right hand side for the same law. I have this universal set U and these two sets A and B. Now here we are talking about B intersection A. So if I talk about B intersection A, it is nothing but again the elements which are common to set B as well as A. So in which portion of my Venn diagram these elements will lie? They will lie again in the center region. So this region is nothing but my B intersection A. So that means A intersection B is the same region as B intersection A. That means the law 3B also holds good for sets. So we can say that commutative law holds for set theory. Now moving to the next law, which is known as distributive law. So again for distributive law we have two parts. First we will try to distribute the union operation, and in the next part we will try to distribute the intersection operation. Now we have three sets A, B and C. First we will talk about this 4A part. So what does it say? That if we have three sets A, B and C and I find out the intersection of B and C first and then I combine it with A using the union operation. So this will be equivalent to A union B intersection A union C. So let's try to verify this law using Venn diagram. So first This is my universal set U, and here we will be having 3 sets, that is A, B and C. Now first we will be talking about this B intersection C. So B intersection C is nothing but the area which is common to both the sets B and C. So this region will be shown by these lines. So this is my B intersection C. Now I have to combine this region or this result with set A using the operation union. That means all the elements which are in set A and in my result. So this will be shown by this thing. So the output for my left hand side is actually this region. This, I am just showing it with the outer lines. This region is the LHS. Now if I draw the RHS for the first law to verify, this is my universal set U, okay, and I'll have 3 sets A, B and C. A, B and C. Now first of all I'll take A union B. So A union B means all the sets of all the elements of set A and set B. So these will be denoted by this, gives my A union B. Now I'll find out A union C. So A union C means all the elements of set A and C. Now we'll combine both the results using the intersection operation. That means whatever we have in A union B and A union C, whatever is the intersection part for that, that is basically the output. So we'll just check in the first in the left hand side of the first part, I have drawn the horizontal lines and then I have drawn the vertical lines. So for intersection, the region where we have both types of lines, so the region where we will have both types of lines is this one. We can see it clearly in the diagram, this one, and this is the same as the left hand side. So we can say that the law 4A holds good, that is the distributive law holds good for set theory. Now talking about the second part of the law, that is A intersection B union C. This is same as A intersection B union A intersection C. So we'll also verify this law. So first we'll draw the left hand side for this 4B. This is my universal set. This I am showing for the left hand side. I have 3 sets A, B and C. Now first I'll find out B union C. So what is my B union C? All the elements which are in my set B and my set C. So if I show it with the lines, this entire thing will come in B union C. Now I have to combine it with set A for intersection operation. So what I'll do, for A I'll just draw the horizontal lines. Okay, so now let's see that which part is being common in both A and B union C. So if I talk about the part which is common in both, that is A and B union C, it will be basically the center part. And even this part. So this is actually there in A as well as in B union C. Now drawing the right hand side, this is again my universal set U, and I have 3 sets A, B and C. Now first I'll find A intersection B. So A intersection B is nothing but this part. then A intersection C. A intersection is nothing but this part. Okay. Now union of both the parts means again this entire region. So this petal like region which was also there in this I had shown, and it is there also in the right hand side. So I can say that both the left hand side and the right hand side are equal, and the distributive law holds good even for the intersection operation in set theory. Now coming to the next law, these are the identity laws. So in identity laws, we have a total of 4 parts. The first law says that if I have a set A and I take the union of this set A with a null set or phi, then I get the set A itself, because null set is nothing but a empty set. And the second part of this law says that if I have a set A and I take its intersection with the universal set means a collection of all the sets under investigation. So whenever I'll take an intersection of any set with the universal set, I'll get that set itself, that is A. The second part of the law, that is 6A, says that if I have a set A and I take its union with universal set, so I'll always get the universal set. And if I have a set A and I take its intersection with phi, that is null, then it is always going to give me null. So to show these laws using Venn diagram, first part, now I have a set A, okay, and I am trying to take its union with a null set or an empty set, then I'll get this region, that is A itself. So I can say that for 5A, I can verify that A union phi is A. Then for 5B, I can verify it as, this is my universal set. I have a set A, and now the common portion in this universal set and set A, intersection means common. So this is again nothing but this A. So I have verified this law 5B. Now coming to 6A, I have a universal set U and I have a set A. Now if I take the union of both these sets, that is the entire universal set and set A, so that means it is going to be the entire region, which is nothing but set U itself. Now coming to the last part of the law, that is 6B. It says that if I have a set A and I try to take its intersection with the empty set or a null set, so since there won't be anything common, the other set is null, so again, I cannot show it in the Venn diagram. It is going to be phi. A intersection phi or A intersection null set will be a null set. Nothing will be there in common for set A and set phi. So these are my identity laws. Now coming to the next law, that is involution law. Involution law says that A's complement, this notation we have used for complement. So whenever I'll take A's complement and again I'll complement it, I'll get the set A itself. Let's see. Suppose this is my universal set U and I have a set A. Okay, so whenever I'll try to take the complement of set A, it means everything except set A. So that means the region other than this set A, all the region other than this set A. Okay, now again if I'll take, this is by A's complement. Now again if I'll take the complement of this A's complement, what I'll get? I'll get the region other than which is in my previous result. So that means I'll get only this thing which is nothing but A. So I can say that A's complement is equal to A itself. So this is what is involution law. So coming to the next laws, these are the complement laws. So the complement laws, we have 4 parts. So the first part says that if I have a set A and I take its union with its complement, so the result which I'll get will be the universal set. The second law says that if I have a set A and I take its intersection with the complement of set A, then I'll get a phi, nothing will be there. If I have universal set U and I take its complement, so I'll get nothing, I'll get a null set. If I have a null set and I take its complement, then I'll get everything that is the universal set itself. So, to show it by Venn diagram, the first part, now this is my A, okay. And this is my A's complement. Now, when I'll take a union of both these, I'll get that is the universal set itself. So, this is the first law. Same way, if I have set A and its complement and I try to take the intersection. So, intersection means the common portion. So, in this diagram, we have only A. In this diagram, we have everything other than A. So, is there anything common? There is nothing common. So, what we'll get? We'll get a null set or a empty set. So, this is my second law. Now, coming to the third law, if you have universal set U, if you have universal set U and you take the complement of the universal set. So, complement of universal set will give me nothing but a null set, and if I have a null set and I try to take the complement of the null set, so I'll get everything that is there in the universal set. So, these are my complement laws for set, and that's all for today. Thank you.